be starting our webinar Beam Focusing in Beamformers in the next minute or so. Welcoming Brian Starkoff to the series this evening. Focusing are familiar with ASM, but for those that you aren't, the Australasian Society. This evening's webinar will be earning you a CPD certificate of 1 CPD point, whether you view it live or view the recording. Before we get started, I'd just like to quickly cover off some housekeeping detail be taken down. We will email you a CPD certificate of 1 CPD point, also approximately 6 weeks from today. And please, can you take a minute and leave us with your honest feedback at the end of the webinar. Please note that you've also joined this webinar in listen-only mode, so everyone has been muted. And if we get cut off, don't worry, we'll dial back in. If you have any questions at all, including any technical queries that you need help with, you may submit these at any stage during the webinar and we'll be able to assist you. For any questions with regards to the topic, those will be saved till the end of the presentation, where Brian will be addressing them in the Q&A session. So just a welcome back to Brian Starkoff to present for us once again this evening. I'm sure that plenty of you got a lot out of his previous presentation that he presented for us on simple transducer design and operation. So Brian, we look forward to what you have for us this evening. And once again, I will hand over to you. Thank you.
Hello there and welcome. Today we're going to get a little bit more involved with the physical principles of ultrasound. And the topics I'm going to look at in this session are particularly revolving around beam focusing. That will include looking at multiple focal zones, variable aperture, which is incorporated in most machines when you're using multiple focal zones. I'm also going to discuss receive focusing, which is quite an interesting concept, and all ultrasound machines will incorporate the process of receive focusing. At the end, I want to touch on beamformers, at least the use of multiple beamformers. Most machines are now coming with multiple beamformers, and it's nice to know the advantages of those. Okay, so let's look at beam focusing. If we did nothing with the beam coming out of a transducer active face, the aperture, the beam would look roughly like what you're seeing on the screen here. It would come out for a distance where the beam would slightly converge, and then it would get to a point and then start diverging again. But generally, the beam is going to be wide, quite wide. We don't want this. We want the beam to be narrowed. And you're going to learn about that when you start to learn about resolution, that we need a very narrow beam to get very good lateral resolution out of your machine. So all our ultrasound beams are focused in something like what's showing in the lower part of this diagram. Now, this beam focusing can be achieved in a number of different ways. It's possible simply to curve the transducer element. Now, curving the element is not easy to do. Physically making the elements is quite difficult, and curving them to a particular radius of curvature is not going to be easy for the manufacturer. So this method is generally not used in modern transducers. It's interesting to note that the first ultrasound machine that I ever used, and I hate to say it, but it was back in the late 1970s, that the transducer elements in it were in fact curved like this, and that's how they achieved their focusing. It was the old UI octasign.
So what's the whole point of doing this?
But as I said, it's not done today.
It's not done today, he's just telling you.
It's much easier to make a flat transducer element.
Well, maybe one day,
So
like 20 years
the
later,
other method of focusing that is used is to use an acoustic lens, which is placed on the face of a flat transducer, and that's able to focus the beam down. Now, this method is very common and, in fact, is still done today in many transducers, if not most transducers. It's not done for our beam with focusing, as we'll talk about shortly, but an acoustic lens is commonly used for slice thickness focusing in most transducers. So, yes, although it dates back from many, many years ago, acoustic lenses are definitely still used today. What it does when you're using a lens, it uses the principle of refraction. So you might have to go back and rethink about what refraction is, how the beam bends if it goes through an interface at an angle, and two different materials on either side of the interface have different speeds of sound. So here, on the left here, I'm representing a concave lens. And in this case, the speed of sound within the lens material is higher than that in soft tissue. So it's greater than 1540 meters per second. And this way, the beam would bend in on itself like this. And I will often represent an acoustic lens in this fashion because intuitively it's easier to sort of see how the beam directs at 90 degrees to the face in like that. But the lens can also be made convex. And if you look at refraction, if the speed of sound in the lens material is lower than that of soft tissue, then the beam will bend in the other direction. And therefore, the lens can be made in this convex shape. Now, in fact, most lenses are made in this convex shape. The reason is if you put this left-hand diagram lens, the concave lens, on the transducer, put gel on the transducer and you put it on the patient, there is a moderate chance that you will get a small amount of air trapped underneath in the concavity. Well, that would be a disaster because the air would reflect the sound and degrade the image quite significantly. So most lenses are made convex like this so that it would push any air out the way and produce a much better beam for you. So, but nevertheless, you'll find that most times I will represent the lens like that simply because, as I said, it's easier to picture. Okay, now another method of focusing was used many years ago, an old technique, but occasionally is still used now, is to use a flat transducer element, that's fine, and you fire the beam out and it strikes a curved acoustic mirror that bends the beam in as shown on this diagram here. Now, well, as I said, it's an old technique, but in some intravascular transducers, they designed these with a curved mirror in them. And the intravascular transducers are the ones with the very small transducer head on them that goes up with inside arteries. But nevertheless, it's not generally used. Now, all those methods I've described so far have a major inherent disadvantage. The curved element, the acoustic mirror, and the curved focused mirror are fixed focusing. Once you create that hard curve in the mirror or in the acoustic lens here, then you're committed. There's no choice, and you can't adjust it. So that is really a problem. The more modern method of focusing your beam in transducers today is electronic focusing. And we're going to learn how they can adjust the focusing in this method. Now, electronic focusing must be done with an array transducer. That is, a transducer with multiple elements within them. If you've got that, then the manufacturers and designers have the option to alter the focus to wherever you want. Now, before we go into that, just a couple of points to make about beam focusing in general. There's a term called the focal zone of a transducer. The focal zone is the depth within the beam or within the patient that the beam itself is less than twice its minimum width. In other words, if your beam width at the focal point, focus down nicely to say 2 millimeters. When the beam is at 4 millimeters proximally and 4 millimeters distally, then that region within there is called the focal zone. And that's the region that you need to be using the transducer. That's where the beam is the narrowest. Once you get beyond the focal zone, the beam is starting to become quite wide. And that, you'll find when you start to learn about lateral resolution, will degrade the lateral resolution significantly. Okay, now with focusing, when you decrease the radius of curvature, that is, if you're talking about, for example, a lens or a curved mirror, the radius of curvature there, if you decrease it and make that curve steeper, then the first thing that will happen is that the focal length will reduce. And in fact, that curvature is in fact the focal depth. So if you bring your focal point up, what you're doing is effectively increasing that curvature. It also decreases the beam width at the focal point. So the closer you get to the transducer, the narrower the beam is at the focal point, which is nice, but sometimes, of course, you need to focus down deep into the patient. But nevertheless, that's another thing that occurs when you bring the focal zone up close to the transducer or decrease the radius of curvature. The third thing that will happen is that your focal zone will become less as well. So all those three things happen. You decrease the focal depth, the beam reduces at the focal point, and your focal zone gets smaller. Okay, now the width of the beam at the is virtually equal to the lateral resolution that's achievable with your particular beam that you're using in your patient. Now, that beam width at the focal point can be calculated. There's a formula. The formula is 2.4 lambda A on D. It's a formula worth remembering because there's a few things that you could glean out of that formula. Lambda is obviously the wavelength of the beam, of the actual pulse that's going out. A is the radius of curvature, which is the same as the focal depth. And D is the diameter of the element, or the active transducer aperture. That is the diameter of the area on the transducer that's producing the beam. Okay, now here's something that people forget about. I think sonographers in general tend to forget about the other plane of your image. Yes, you're always looking in the beam width plane, that's fine, but you've always got slice thickness to consider. And it's rather important at times. When you learn about various resolutions, particularly contrast resolution, slice thickness is very important. So this beam width formula also applies in the slice thickness plane. So as long as you know the thickness of the elements within your transducer, that is D, and you know your focal depth, and you know the frequency of the transducer that you're using to calculate the wavelength, you can actually calculate the slice thickness at any point in the beam itself. But certainly do keep it in mind that the beam width formula is available to use in both the imaging plane and the slice thickness plane. Now, this is something that you may come across when you scan. You should know from the formula, the power intensity formula, that the beam intensity increases within when the beam width decreases. In other words, in the focal zone, because the beam width is getting smaller, the actual intensity of the beam is increasing, because intensity is the amount of power in the beam divided by the area of the beam. So obviously, if the area of the beam goes down, then intensity will go up. Now that can cause, on some images, an area of brightness within that focal zone, as shown on the right over here. Now normally that won't occur because it's usually corrected automatically by the machine itself. As soon as you put a focal zone at some point, the machine will apply some TGC to reduce the gain within that band that you put the focal zone. But occasionally you might find that the automatic system doesn't work well enough, and you will see this band of brightness on your screen. If you see that, do not necessarily consider that to be pathology or change somewhere in the tissue within that. Just have a look for where your focal zone is, and then you may need to manually correct your TGC to get rid of that band of brightness. So just something to keep in mind. But it's not any failure particular of the machine, it's just the automatic function, although working, hasn't quite worked well enough to correct for it. The other way, you could either manually apply some TGC there, you could also increase the number of focal zones, which will spread it out over that area and increase it generally. But you should be able to manually adjust that out. Okay, now let's have a look at this electronic focusing. This is the focusing that's used on every imaging transducer today. Every imaging transducer will have electronic focusing on it. I'm not going to talk about continuous wave transducers. That's a different field in cardiac ultrasound, and they don't have electronic focusing. But all our transducers that produce images will. So it's by far the most common type used today. What they do is they don't necessarily fire all the elements in the multi-element transducer at the same time. They can delay the firing of the inner elements. Remember, with electronic focusing, you must have an array transducer. You cannot do this with a single element transducer. Now let's have a look. Here's a diagram of a transducer with most of the innards removed. I haven't got the case shown. I'm just showing the multiple elements across here. These lines here are simply the wires going down to energize the individual array elements. I haven't got showing damping material, and I am not showing matching layers, lenses. Well, there's no lens here on this particular case anyway, but none of that. It's just the inside work of the transducer. Right. Now this little 90-degree V here is a representation of the electrical voltage that's being input from the machine. And it will come down the line and go to all the elements, energize them, and make them vibrate, and send out their sound waves. Now, if we did not use focusing at all, what would happen is the signal will come down, go into this splitting area. It would break up into signals that will go along all these individual wires here and go down and energize all the transducer elements at the same time. What would happen then is that each wavelet, or each element's wavelet, would come out at the same time like this. and then they would join and the wavelets would produce the overall beam, add together by wave interference, and the resulting beam would be a non-focused beam. Again, just a little bit of reminder about beam profile. Just remember that a non-focused beam will in fact converge slightly. Even though it's just coming out unfocused, it will converge slightly to a certain point called the transition point before it starts to diverge out. But you may like to go back, pick up a textbook and refresh your mind about beam profiles, about near field and far field length. Okay, so we've got a non-focused beam, but we want to focus it. So what the designers came up with is that they added a circuit into the beam circuitry, beam formation circuitry. It's a delay circuit. Now I'm showing it just here within the transducer itself, as beam comes out, but all of this will be happening within what's called the beamformer. So I'll mention beamformer again a couple of times. The beamformer is a circuit within your ultrasound machine that looks after the individual energy spikes going into the individual transducer elements and the timing of them. Okay, so with a focus transducer, as I said, they've added this delay circuit. And this delay circuit can apply delays, electrical delays, to the energy coming down through these wires. So what will happen here is you will have your main energy spike coming from the machine. The machine says, right, I'm sending out a pulse now. So down it goes. It splits it up into the individual wiring elements, which will come down into the delay circuit. Now, at this point, the delay circuit says, right, I'm going to allow the outer element voltages to go straight through and energize the array elements down here. But I'm going to hold up and stop or delay the inner elements, the voltages to them, by just a little bit. So you'll wind up with the electrical voltages coming down in this sort of a pattern. So as I said, the outer elements will arrive first, followed immediately by the next elements in, and so forth, with the central elements here receiving the most delay. Do keep in mind that these delays are very small. The electrical voltages are extremely close together time-wise. They would be nanoseconds apart, okay? So very close. So they've come down here. So what will happen now is that the outer elements are generating their little wavelet first, followed by the elements immediately next to them towards the center, and so forth. So all the wavelets from the elements will come out in this sort of shape. Now those wavelets are going to add together with wave interference to form a final wavefront. There's a law of physics that says a wave will always travel at 90 degrees to its wavefront. So if you can force the wavefront to a different angle, that's the direction that beam will travel. So this side over here of this final wavefront will travel inwards. The wavefront on this side of the transducer, on the right of my screen, is angled differently, and it will travel in the direction shown by the arrow. In other words, the two sides of the wavefront are forcing the wave in on itself, and the beam focuses. Very clever indeed. So now, without putting a lens on the transducer, without curving the transducer elements, they have managed to focus the beam simply by manipulating the way these little wavelets come out from the transducer itself. So brilliant. Now here's where the real magic starts. It's adjustable. all you have to do is make changes to the delays that are being applied to the transducer elements, to the voltages going down. So as you can see on the left here, the delays are more marked, and it gets less as we move to the right. That electronic circuit that I mentioned before, the beamformer, makes these delays for you. All you have to do is move a toggle on your machine to say, I want to focus at different points in the patient. That tells the beamformer to adjust the delays within this circuit here, the delay circuit, to change effectively the radius of curvature of that beam front that's going to be coming out from the transducer. Therefore, you can make that beam focus to whatever depth you want in the patient. So increasing the delays, as on the left over here, making them further apart from the first wavelets come out to the last ones, results in a couple of things. First, because the radius of curvature now has decreased, the focal point moves up closer to the transducer. You get better focusing at the focal zone itself, and one of the results of that is you do get a shorter focal zone. Okay, so that's what happened. As you decrease the delays, as you can see, the opposite occurs. The focal point moves further away, and the beam gets a little bit wider at the focal point itself. But that's quite brilliant. Now, once you can do this, then they realised, well, how about we send out along the same beam path, one pulse following the other, but at different focal points. This results in the use of multiple focal zones. And I've got here, most ultrasound machines now allow the use of several different focal zones. I would have to say at this point that all machines I know of will allow the use of multiple focal zones. This is how it works. Now, a separate pulse must be transmitted for each focal zone. So the machine at first sends out a pulse with fairly increased delay set on the delay circuit, which means the focal point is up close to the transducer. Right, so it's going to focus fairly close to the transducer, or certainly closer than anything else to the transducer. Now, what the machine will do is will say, I'm only going to listen to the echoes to come from a certain depth, not the whole field of view depth that you've set. I'll only wait for the echoes to come back from, say, the depth that I'm showing here. It will then stop listening, get those echoes, and move it over into the image memory of the machine, the computer storage area, or the image memory, and hold it there and keep them. It will then not move the beam path, keep the beam path exactly where it was in the patient, and it will send out another pulse. But this time the delays are set slightly differently. The delays are slightly less, so that the beam will focus at a slightly deeper depth. Now the machine says, I've already got the echoes down to this depth. I'll now receive echoes from that previous depth, start listening at that point, and receive echoes down to the next point, as decided by the machine. It will keep those echoes and put those into the image memory and match them up with the ones that it's stored there from the previous pulse. And then it might send out a third pulse. Again, the delays are less again. It will be focused deeper down. It will take the final lot of echoes from deep in the patient and store it in the image memory. And it will put those all together into the echoes from that one beam path. Now you can see here on a representation, hopefully, that you will now have a narrow beam through throughout the whole of your depth of field of view. Excellent. So now you've got good lateral resolution all the way down. The compromise is it takes longer to do it. In this particular case, I'm showing 3 pulses coming down in the patient. So the frame rate is going to be reduced quite significantly. And that's just a compromise you have to put up with if you're using multiple focal zones. Remember, they can be switched on or off. You don't have to use them. It's up to you. Some machines might set up to 9 focal zones for you to get really good narrow beams all the way down through that image. Now, just taking my example here of 3 focal zones, you would probably theoretically say, oh, well, my frame rate is going to drop to 1/3 of what it could be, because it's got to send out 3 pulses along the line. And in fact, the first machines using this technique, that's what they did, because the machine would wait for the full depth of field of view each time it sent out a pulse. But then the manufacturer said, now hang on, we don't have to wait all the time for that full depth of field of view before we send out the next pulse. So what they do now is that they'll send out the first pulse. It will stop listening at this point, as I've described before, but it will immediately send out the next pulse, which is faster than what you would normally do for a full field, for a full depth of field scan line. So it sends out the next pulse, it would stop listening at this slightly deeper depth, and then it would immediately send out the 3rd pulse. So they can get a little bit quicker. With 3 pulses per line, you might find your frame rate will drop by half, not to 1/3. So they can help a little bit, but reduced frame rates are a result of using multiple focal zones. So if you happen to want high frame rates for something, you tend not to use multiple focal zones. Nevertheless, for most things in ultrasound, which are relatively slow moving, then the use of multiple focal zones is a brilliant feature because it gives you very good resolution, lateral resolution down through your image. Now, to help a little bit further, particularly with the beam profile up close to the transducer, they can reduce the beam width right near the transducer by not using all the elements for the first pulse. Now, this will only work when you're using multiple focal zones. But what will happen with your first pulse, which is focused up close to the transducer, then they'll only use the inner elements. And that will create a narrower transducer aperture, which is the active face, and therefore the initial beam that comes out is slightly thinner. Now, for each successive focal zone then, as it sends out the second focal zone, which is focused deeper, then it will use more elements. So at this point, it will widen out the transducer aperture, the active face of it, a bit more, so it will get better focusing down deeper, because remember your beam width formula. The problem is that if you use a small diameter aperture on your transducer, which is what D is here, if this becomes small, as shown on the first image over here, beam width increases because it's below the equation line. Therefore, if you decrease the aperture, the beam width at the focal point is going to be wider than what it could be if you used a wider aperture. But when you're up close to the transducer, it's not quite so important because you've got very good focusing at that point anyway. And you'll find that will be fine. It can sacrifice a little bit of beam width here if you can make the beam smaller in the area up in front of it. But as you go down deeper, the beam width becomes more critical. At this point, you need to increase D to make the beam width smaller. So once you start to go deeper, you will need to increase the aperture to get a decent beam width at the focal point. And when you get really deep, they'll be wanting to use as wide an aperture as they can, because that's where you're going to get your best beam width when you're deep down in the patient. So you'll find when you're scanning deep into the patient, then that's going to be important. Now, here's another interesting point, dynamic receive focusing. Once the beam has gone out and it's getting echoes coming back from the patient, what will happen is that you can also focus the echoes. You say, how can this possibly happen? It's done, I think, personally, by physics magic. It's wonderful. What you do is you delay the signal processing between the elements when the actual echo comes back. In this ideal situation that I'm representing, the wavefront in an echo would be flat. This is ideal, it doesn't occur. The wavefront would come back up, hit all the elements at the same time. All the little electrical signals would come up and at the same time. They would then move up into the addition circuit, and what will happen then, they'll be added together and you'll get a nice big single voltage coming back up. Unfortunately, what happens is that when an echo comes back from a point source in a patient, the wavefront radiates out in this curved fashion. So the wavefront of an echo is curved. Now, in this case, if this happened, the curved front would hit the inner elements first, and the little electrical signals will come up in this fashion. When they move up into the addition circuit, they will gradually add up together over a short period of time and get a longer, lower amplitude output signal voltage into the machine, which is much worse from your echo point of view. So they said, well, hang on, we can correct that. We've got a delay circuit built within the beamformer. So as long as we know how much to delay the inner elements, we can let the signals catch up. Watch. Here's our wavefront coming up, and here are our signals coming up in this curved fashion. So they're separated by short time delays. When they move up into the delay circuit now will hold up the voltages within this little central area, allow all of them to catch up with each other, add together into a single big output voltage. Beautiful. So even though you've got a curved wavefront, you get this nice signal, providing the delays are set correctly. But to set the delays correctly, the machine would have to know the radius of curvature, wouldn't it? Logically. It does. The radius of curvature is the focal depth, or is the depth that the echo came from. The machine knows where the echo came from. It's done the timing. After all, it's going to put that echo in the right point on your screen. So therefore, the machine knows from its timing what that curvature is, automatically sets the delay accordingly, and gives you the best signal. So as the echoes come up from deeper and deeper, the delays are automatically adjusted less and less to maintain that signal. So here we've got the delay set quite markedly because the echoes are coming from superficially. Here, the echoes are coming from deeper. The machine knows this, and therefore the beamformer will automatically set those delays accordingly. Isn't that clever? You're getting maximum amplitude signal from the echoes, no matter where they're coming from in the patient. Okay, just to further improve that, the machine may also use dynamic aperture. Now this acts very similar to the aperture, variable aperture that I've already described, so that the echoes coming from near the transducer, they don't need the other elements and only use the inner ones. And then gradually it will use more and more. So this may be used as well, but that will happen automatically gradually through the receipt of all the echoes throughout that whole length of field of view of that beam path. Now, receive focusing is automatic. You do not adjust it. The machine will just be doing this for you all the time. Now, what happens if the echoes are coming from the right depth, but they're slightly off center? Okay, they're away from the center of the beam. Well, if there's an echo coming from out to the side, it will radiate out its wavefront, but can you see that it will be asymmetrical? It'll be coming up in this sort of shape and hit the transducer elements off center like that. The signals coming up from the individual wires will look something like what I've just showing on this diagram. When they go up into the delay circuit, the delay circuit's set for a symmetrical beam coming from the center here, not for this asymmetrical beam. Therefore, the voltages after the delay circuit will not be all nicely lined up. They will be off center like this as well, and they will produce a lower amplitude signal. So as soon as the echo moves away from the central beam path, the echo amplitude provided to the machine falls off significantly. It'll only give you the best amplitude from echoes coming from the center of the beam path at the right depth. And isn't that focusing? So that's what receive focusing is. That's quite clever. Now, I said that I would mention multiple beamformers. I've already mentioned how the beamformer will adjust those delays accordingly. Make sure that they're all set for the depth from which that echo is coming from. However, what if you had a beamformer, another beamformer in the machine, and the delays were actually set to suit this off-axis wavefront that's coming up from off-center echoes? In actual fact, if the delays here were set accordingly, then any echoes coming from this beam path here, shown as number 2, would add up to a beautiful, strong signal, wouldn't they? This beamformer would not show you or give you a good signal from the ones straight down at 90 degrees because the delays are set wrong. So a second beamformer could be used to detect echoes only from this beam path, the correct depth, but along that line. A third beamformer could be used to look at echoes coming from another beam path. And these delays would be set for this off-center echo with its asymmetrical wavefront looking in that direction. So suddenly you could have 3 beam paths recorded simultaneously by the machine if you had 3 different beamformers. And that's what machines are coming with these days. So each of these beamformers would be looking after just one beam path. And this technique of using multiple beamformers will be used in modern machines these days. There is a theory, and they're working on it now and using it, that if you didn't use transmit focusing and you just flooded the patient with a pulse of ultrasound, you could use hundreds of beamformers to look at all the individual beam paths at the same time. And you can imagine what frame rates would be like. Instead of having a frame rate of 50 cycle or 50 frames per second, you'll be getting a complete frame at the pulse repetition frequency of something like 500 to 1,000 frames per second. When you learn about things like shear wave elastography, you'll learn that extremely high frame rates are needed. And that's what they're developing now, that they can use a lot of these beamformers. It's expensive. These beamformers are fairly complex circuits, but it's worth it. So you could find that if you've got a high-end machine, that you could have multiple beamformers in that machine. And your frame rates in that machine are going to be very, very good indeed. So these multiple beam paths can be detected if you've got the money to buy a good machine. Even if you've got, I'm shown so far, a sector transducer, but a linear array transducer can also utilize multiple beamformers, and it can be, the beamformers here can transmit and receive from just one section of the transducer. For example, beamformer 1 might look after the transmission and receipt of echoes from just this little segment of the linear array. Beamformer 2 would be the next segment. Beamformer 3 would look after the next segment. And they would be, all those echoes would be put together in the image memory to produce your full frame. In other words, it's taking a third of the amount of time to produce the complete frame. Therefore, your frame rates are going to be much, much better. Okay, so multiple beamformers are superb. You could find that your machine that you're using will have those. If you're using a fairly simple machine, it probably won't. Okay, so over to you. Hopefully you've got a few questions about beam focusing, and I'm happy to affront them and see if I can answer them all right for you. Thank you.
Fantastic. Thank you so much, Brian. As per usual, you're always so good at teaching it.
So one particular manufacturer will call a particular feature a particular name, and another manufacturer will call it a completely different name. And I'm sorry, I'm not familiar with the term X-frame.
No problem. We'll move on to our next question. The next question asks, how thin can the beam be focused to?
Now, that will depend on quite a few things, obviously. The beam width at the focal point depends on things like the aperture, the focal depth, and the basically the depth of field of view, the depth of the focus itself. So, look, for example, let's pick an example. Suppose we had a 5 megahertz transducer, and we had the transducer was using a 3 centimeter active aperture, which is quite reasonable, it's fairly wide, but the transducers will tend to use as large a one as possible, depending on where they're focused to. And then suppose we focus down to a depth of, say, 8 centimeters, which is reasonable. If you did that and you did the little beam width calculation, you would find that the beam would actually focus to a touch under 2 millimeters, close enough to 2 millimeters, which isn't too bad, not great, but pretty good. If you went to a 10 megahertz transducer at exactly the same, under the same conditions, it could focus down to 1 millimeter. So it depends on that. Higher frequencies will focus better. And again, as I mentioned in the presentation, if you're focusing up shorter or closer to the transducer, then it will be narrower again. But remember that is at the focal point, the narrowest point. As soon as you move away from the focal point, of course, the beam is going to be wider. So that's fine to have 2 millimeters at the focal point, but when you move to, say, the proximal or distal part of the focal zone, the beam could be 4 millimeters, and it could be wider than that, depending on the conditions. So you can get very narrow beam widths under ideal conditions, but generally, the beam widths are significant. You're going to be looking, 1 to 3 millimeters or something like that.
And I do apologise, the storm is just rolling in where I'm at in New South Wales, so apologies for any background noise you may hear. Exactly. We got some backup, so we should be okay. All right, so you asked that the beam is focused in 2 planes, imaging and slice thickness. Which one is most important for the image?
Well, they're both important, but in different ways. As far as spatial resolution, the detail you can see on the image itself, then the focusing in the beam plane, that is where usually your electronic focusing is being done, it's the most important. The more you can focus down there, the narrower you can make the beam, then that is where the beam is going to give you the best resolution spatially. So in that respect, the beam width focusing is the most important. But when you come to contrast resolution, and this can be important because if you have poor contrast resolution, you might not be actually able to see quite a large lesion or structure in a patient simply because it's similar in echogenicity to the surrounding tissue. At this point, slice thickness now becomes more important, and it is really important to get a very narrow thickness of slice in this to and fro plane, orthogonal plane. So in that case, your slice thickness focusing is more important. And remember, most machines and most transducers will do that with the lens, and it will be fixed at a specific point as set by the manufacturer. And the other thing I didn't mention is that it will be fairly weak focusing. It won't really focus the beam down hard to a very narrow point. It will just bring it down a reasonable amount. So slice thickness focusing is the most important for contrast resolution. Beam width focusing is the most important for spatial resolution. So I hope that answered that one.
Enough time for just one more question, and that one, this person asks, is the delay circuit inside the transducer itself?
Now, I probably did mention that, but I may have skipped over it in the presentation. The way I've presented the actual diagram, it looks like it's in the transducer, but it's not. The transducer is really the last little bit where those multiple wires go down towards the individual elements themselves. So that delay circuit is in the beamformer, which is in the main body of the machine, in the circuitry of the machine. That's where it all takes place. Once it comes out the beamformer, it comes out as individual circuits or wires that goes to the transducer down to the individual elements from there. So it's in the machine.
Okay, thank you so much, Brian.